Welcome to part 2 of understanding the concept of derivative. In the previous video, we discovered that there's a way to approximate how fast an object is changing at any given time, but if we use the average rate of change algorithm, it falls apart because we're forced to divide by 0. So right now we cannot find exactly how fast the area is decreasing at this exact size, even though we can get a fairly decent approximation. But in mathematics, we're interested in precision, and if we want to know precisely how fast we're going, we have to solve the problem. How do we figure this out when the change in x is 0? So this is what the great minds before us came up with. For starters, what they did was they took a picture of, or they took any function, and then they took two different moments in time for that function and calculated the average rate of change. So this formula right here gives me the average rate of change from x1 to x. In other words, this formula here tells me the slope of this secant line. Now, this is the exact same graph, talking about the exact same slope and everything. The only difference is the notation is slightly different. Now, there's a reason for this, but suffice it to say that these are two ways of saying the same thing. Where here we have x and x1 as an interval, and it shows we can calculate the average rate of change by looking at change in y, which is right here, over change in x, which is right here. The same thing can be said this way. Instead of x, we can, or instead of x1 or whatever, we can let this be x, and then this be x plus some other amount. That we call h. So h is the interval between the two x values. So this is f of x plus h, that's the y value when x is h bigger, and this is the y value when x is x. So change in y will be f of x plus h minus f of x will give you the difference here, and then the change in x will be x minus x plus h, which is this guy right here, so to speak. So anyway, these are two different ways to find the average rate of change. And as we mentioned in the previous video, I mentioned in the previous video, when we allow the change in x to be 0, this thing doesn't work. So here's what they decided to do. They use this concept called limit. And the limit concept essentially is, well, maybe we can't let change in x be 0, but what we can do is to let change in x be infinitely close to 0, and we can use what happens to the function as x approaches 0 as a way of finding this instantaneous rate of change. That's a lot to wrap up, and how we actually do the mathematics is for a later video, later time, later lesson. But for right now, what I want you all to understand is we have a way of calculating average rate of change, but if we let the rate of change, the interval of x change become 0, we have to use something more sophisticated in order to find the slope of this line. More vocabulary, this line is a secant line, and its slope of the secant line is your average rate of change. This line only crosses the graph at one point. It's called a tangent line, and we're not interested in the slope of the secant line this time. We're interested in the slope of the tangent line, which will tell us how fast we're going. Now, this is some highfalutin mathematics, but let me show you what happens in terms of our language. If we take change in y over change in x, which is again using that formula I showed you previously, that gives us average rate of change. However, as soon as we apply this concept of limit, now it's no longer an average rate of change, but it's an instantaneous rate of change. So instead of delta y over delta x denoting an average rate of change, we have dy dx, which is talking about an instantaneous rate of change. Instead of using dy dx for delta y delta x, sometimes people use f prime of x. So if the function is f of x, then the instantaneous rate of change is found by f prime of x. Now, there's a lot of stuff to unpack here, but what I'd like to do now is just to get an understanding of what a derivative is and what it's telling us. Just to kind of point this stuff out, there's some synonymous phrases or terminologies which are all sort of saying the same thing. All of these are synonymous with the phrase derivative. When I talk about a derivative, I'm talking about an instantaneous rate of change of a function. That is to say, I'm talking about the slope of a tangent line. In other words, instantaneous rate of change is another way in physics to say instantaneous velocity. That is, how fast are we going at an exact moment in time? Not an average over a period of time, but a speed at an exact moment of time. So instantaneous rate of change, aka instantaneous velocity, aka the slope of the tangent line. So however steep this line is, that tells me how fast the function is going at that point. Another way to say all of that is dy dx. We don't say dy over dx, we say dy dx. Or another way to say all that is f prime of x. So these are all sort of synonyms for the same concept. So to make this easier to comprehend, because all of these different synonymous ways of saying the same thing could get a little bit confusing. So we need to talk about what a derivative is versus what a function is and what they tell us and everything else. So when we studied functions, we would be able to do things like this. We shoot an arrow up in the air, and then we can record the height of the arrow over time. F of x tells me the height of the arrow at any moment in time. When x equals 8, I follow it up to the graph and say that the arrow was 200 feet up in the air. So that's what functions do, and that's what we've studied in the past. Now we're going to talk about calculus, and what does that tell us? So in the figure shown, f of 3.5 represents the height of the arrow after 3.5 seconds. So I go 3.5 seconds, follow it up to the graph. F of 3.5, it's going to be around 350 or so feet. That is how high the arrow was at 3.5 seconds. On the other hand, f prime of 3.5, that's how we say that, f prime of 3.5, or the derivative at 3.5, is not talking about the height of the arrow at 3.5 seconds. It's talking about the speed at which the arrow is moving at 3.5 seconds. The slope of the tangent line right here is, in fact, the exact speed of the arrow at 3.5 seconds in time. With that in mind, you can answer a question. Does the arrow ever stop moving before it hits the ground? Normally you'd say if you shot an arrow up, you see it moving all the time. You never see it stop. But if you understand that slope represents speed, then at this point in time, where the vertex of the parabola is being reached, the tangent line is horizontal. The slope of a horizontal line is 0, which means the arrow was moving 0 meters per second at this precise moment in time. It didn't last long. You can't even see it stop, but it has to. It's increasing in height, it stops, and then it decreases in height again. So that's why we have derivatives. We can actually tell when a function is going uphill or downhill or stopping in midair based on how steep the tangent line is of that graph. That enables us to describe speed as a number or a value, and we can compare one value to another. For example, if these are A, B, C, D, E, and F, we can arrange these in order from the smallest number to the biggest number. F prime of 4 is the slope of the tangent line when x equals 4. That's the steepest part of this curve out of all the ones that are shown, and it's negative, so it's the most negative, which means it's the smallest number. So even though the arrow is moving fast, it's moving fast downhill, therefore the value representing f prime of 4 is the smallest number. F prime of, or actually the average rate of change between 3 and 4 is the slope of this secant line right here. That's going to be slightly bigger than the slope of the line here, and so on. So we get the largest value is C, which is A, B, C, f prime of 1. F prime of 1 is the steepest positive slope out of all of the slopes that we have to choose from. So to try to get all this stuff sorted out, you're going to basically need to struggle with some problems and some questions. And so what we really want to do is, before we start finding what a derivative, or finding a derivative, we want to know what a derivative is. And so the exercises provided here are all designed, and they're on the PowerSchool Learning page, but everything here is designed to get you to understand the language and the meaning of this thing called derivative. So I hope this video is helpful in just sort of summarizing some of the major ideas. And if you pause the screen here, you'll get a really good understanding of the nuts and bolts of a derivative, and then here also a good chance to understand what derivative is. So if you wanted to pause and reread or watch the video again, hopefully that should help you. Thanks a lot for watching.